Hello everyone, welcome to Making Your Knowledge Graph, LLM-Ready, Quality Assessments and Design Strategies for GraphRAG. This session will be presented by Panos Alexopoulos. So over to you, Panos.
Thank you, Daniel. So, hello to everyone. Good morning from the Netherlands, and I guess you're all around the world. So, let's start. Let me share my screen. Okay, so in today's talk, I'm going to focus on the role of knowledge graph quality when it comes to using it in conjunction with large language model, and particularly when using it in the context of GraphRAG. A bit of clarification. The initial description of the talk was meant for a 2-hour workshop, so it's a bit more ambitious, but ultimately because of time limitations and resource limitations, it's going to be more of a high-level talk. So what we're going to talk today about is 3 things. So we're going to see a very brief overview of what GraphRAG is, what it entails and how it works. Then we're going to see to talk about how can we assess GraphRAG quality, what metrics can we use, what these metrics can tell us, and how from these metrics we can determine or at least suspect whether our knowledge graph needs to be improved or not. And finally, we're going to see what are some typical quality issues that might happen in knowledge graphs and how this may affect the overall quality of a GraphRAG application, and some high-level methods on how to detect those. Before that, let me introduce a bit more myself. So I've been a data and AI practitioner, author and educator for the last 20 years. I started working with ontology and knowledge graph back in 2004, far before the era of, let's say, the rebirth of machine learning, big data, and now, of course, LLMs. At the moment, I'm working as a lead semantic data and AI solutions at EEBV. It's a small consulting company in the Netherlands, where we work with clients, big organizations, to help them with implementing knowledge graphs and data integration solutions. In 2020, I wrote a book with O'Reilly on semantic data modeling, covering best practices and how to avoid pitfalls and how to address things when we build knowledge graphs, ontology, and generally semantic data models. And currently, I'm writing a new book on evaluating AI systems. So let's start. When we interact with an LLM for question answering, and generally the typical way we interact is that we give it a question, the LLM takes it and gives us an answer. So that's the simple thing, and actually that's the most, let's say, appealing thing when it comes to an LLM. However, it has been found through experience that this simple approach suffers from several drawbacks. One being the famous hallucinations, of course, of LLMs, the fact that they cannot always be trusted for telling you something that is correct. The second thing is the problem of knowledge cutoff, the fact that we cannot always expect that a large language model will know, will have information about our particular domain or about our particular knowledge and documents that perhaps are not accessible. And a third limitation is the lack of explainability, the fact that we can get an answer, maybe even with an explanation about this answer, but this explanation might not be as trustworthy as we would like. For that purpose, the communities and the industry has come up with an approach called retrieval augmented generation. The basic idea behind this approach is as follows. We still want to use the LLM, but we want to give it concrete additional knowledge, external knowledge, that might not be in its training data already. So in the typical RAG, in a typical RAG pipeline, this external knowledge is in the form of documents. So the way a RAG architecture works is as follows. We have a question, and we feed this question. Before we feed it to the LLM, we give it to a retriever. The retriever, it's actually an information retrieval system, a search engine if you like, which from the documents that are in our external knowledge base will retrieve the top K, usually similar documents, similar to the question. These documents, these top K similar documents will form the context of our question, and along with the question will be fed to the LLM. So, and then the LLM will use this context to reason and answer the question. The idea, what we expect from this is that because we give it particular context to the LLM, that we will reduce as much as possible the probability of hallucination, and that will increase the chance that we'll get a meaningful answer. Now, GraphRAG is a variation of this main of this architecture, of this pattern, where the main difference is that instead of using documents as our external knowledge, we use a knowledge graph, right? I'm not going to define again a knowledge graph. I assume that attending this conference, you have already some knowledge of what a knowledge graph is. But again, the idea is that a RAG with a knowledge graph has the same interaction paradigm more or less, and uses a knowledge graph as an external knowledge source. Now, there are several variations of GraphRAG, but the two basic patterns that we have seen being used are as follows. The first pattern is called text to query. Here, what we have is that we have a user posing a question. And what the system does is that it retrieves from our knowledge graph its schema, so only its schema, not its data, which means that the type of nodes, the labels, the properties, and the relations, and uses the schema to transform the question into a structured query. If we use Neo4j, that query would be cipher. If our knowledge graph, for example, is in RDF and semantic web languages, that query would be a Sparkle query. If our knowledge graph for some reason is implemented in a relational database in SQL, then the question would become an SQL query. The second pattern is more, let's say, similar to the traditional RAG. This is when we consider facts and assertions from the knowledge graph, either from the whole knowledge graph or a subset of it. We create vector embeddings for these facts and assertions. We store them in a vector database, and then given a question, we perform a retrieval of the most relevant facts based on embedding-based similarity, right? So this is a different pattern than the previous one. It has its pros and cons with respect to the previous one. Now, GraphRAG quality. How do we know, how can we assess whether a GraphRAG system works well for us? So there are three quality factors that we need to consider, right? If I go back, we'll see that when we have a RAG system, we can view it as end-to-end, so question and answer, but it also has three important components. It has a retriever, it has a generator, and it has an external knowledge. The quality of each of these components will inevitably affect the overall quality of the system. So, when we assess a GraphRAG system, the quality of a GraphRAG system, we need to consider the quality of the retrieval, that is asking the question whether the retriever retrieves useful and relevant context for the user input, for the user question. The second thing is the quality of the generation, that is whether the LLM understands and uses this context properly. And finally, the quality of the knowledge graph itself. So whether the structure and content of the knowledge graph actually helps the retrieval and the generation steps or hinders them. So how do we know what works well and what not, right? How can we assess if the overall system works well or not, and which of these components might not be working so well? For that, we have metrics. In retrieval in RAG systems, there are several metrics that have been proposed by the community and are available in several toolkits. I will talk here about 6 of these. First metric is called answer correctness. This is an end-to-end metric that practically measures whether the generated response to the question is factually accurate and complete with respect to a ground truth answer. So in order to calculate this metric, we need to have for a given question its ideal ground truth answer, and then what we do is that we take the actual answer that the system gives us and compare it to the ground truth answer, right? So this is an end-to-end metric. This is a useful metric to evaluate whether our system works well or not, but it's not really useful for debugging purposes, which means that if for some reason we get a low answer correctness, we cannot know just from this metric whether the problem is in the retrieval, whether the problem is in the generation, or whether the problem is in our knowledge graph. A second metric that is quite helpful is answer relevance. This one measures how well the generated response addresses the user query and aligns with its intent. This is similar to the correctness, but the main difference is that we don't have a ground truth answer. So the only thing that this tells us is whether the answer that we get answers the question, but not whether it's actually correct, right? Or whether it's the exact is actually the answer that we are looking for. A third metric is faithfulness. Faithfulness measures the extent to which the generated answer is factually consistent, not with the question, but with the retrieved context, right? Because it can be that the answer that we get is contradictory to the context that we got, or it's neutral, or that it is entailed. A fourth metric is contextual relevance. This one measures how relevant the retrieved context is to the input question. Similar to contextual relevance, we have contextual precision and contextual recall. Contextual precision measures the extent to which the retrieved context is relevant to the expected output. So also for this metric, we need a ground truth. We need to know for a given question what is the expected output. And similar for contextual recall, we measure the extent to which the retrieved context includes all the information needed in order to produce the expected output. Now, the power of these metrics is actually, the usefulness is when we actually combine them. So let's see some basic scenarios. Let's say that we measure these metrics and we find that we have a high answer relevancy and low faithfulness. This means that the generated answer is well aligned with the user's question, so it does answer the question, but it is not actually supported by the retrieved context. So the retrieved context says something different than what the answer tells us. This indicates hallucination in the generation step, right? It's not that the retrieved context is relevant, so it's not a retrieval problem, but the fact that the answer is not faithful to the context indicates that the LLM has actually, let's say, practically ignored the context and has decided to give us its own answer. A second scenario is when we have low answer relevancy and high contextual recall. That means that the context is relevant, but the generated answer fails to address the user's query. So it's an answer to another question practically. Again, here, the problem likely lies in the generation steps. It's not the retrieval, it's not the knowledge graph. A third case is when we find low contextual precision and low contextual recall. In that case, then it means that the context is wrong and most likely insufficient. Here, the likely cause is a retrieval failure or a wrong or incomplete knowledge graph, which means that we need to further investigate. Now, the question I get many times from people who build RAG system, GraphRAG system, is what can be wrong with my knowledge graph, right? Because there is this, the articles that I read online and the proponents of GraphRAG, they say that with a knowledge graph is good, is perfect, and works very well with the LLM. The thing is that in practice and from my experience, and I guess many of other people's experiences, there can be many things potentially wrong with a knowledge graph that we need to be very careful of. And I would summarize here, I would say there are 6 main categories of problems in a knowledge graph. The first potential issue is having a knowledge graph that contains assertions, facts that are plainly false, or if not plainly false, highly subjective and debatable, right? So having, for example, let's say that we have a geographical knowledge graph that links countries to cities, for example, right? And saying, for example, that the capital of Greece is New York, right? That would be obviously wrong. So if we have a knowledge graph with wrong facts, with wrong assertions, this will provide wrong context to the LLM and to the RAG system, and therefore the accuracy, the correctness of the answers will be compromised, right? It can also be, however, that the assertions are not technically wrong, but they can be highly vague and debatable. What does that mean? Let's say that we have a knowledge graph about professions and skills, and we want to use this graph in order to provide career advice. So we have a question saying, okay, can you tell me what skills do I need in order to work as a data scientist or as a knowledge graph engineer? Or what skills I must have? And assume that the knowledge graph contains this relation between professions and skills. Now, there is not a universal truth about the relation between a profession and a skill. This can be highly subjective in the sense that it can be dependent on context, it can be dependent on industry, it can be dependent on country, right? So it might be that the knowledge graph seems to contain relevant knowledge, but if the agreement as for the correctness of this assertion is not high enough, then again, the correctness and acceptability of the overall system may be compromised. A second issue when it comes to knowledge graphs can be knowledge that is inconsistent. That is having in the same knowledge graph assertions that semantically contradict one another, right? For example, going back to the example with geography, imagine having an assertion that a country has 3 different capitals, for example, right? The problem with this semantic contradiction is that they can confuse the LLM as well, right? So imagine that you retrieve a context that contains 3 contradictory facts, right? The LLM will not have a way to distinguish between the 3, so there's a high likelihood that will give also a wrong answer. A third topic, a third problem is missing knowledge, right? The knowledge graph there's a high likelihood that it's not fully complete, that it doesn't contain the assertions that actually should be there, right? And when that happens, there are two potential outcomes. Either the retrieved context will not be there, so there's no context to be retrieved, or the retrieved context will be most likely irrelevant to the question, because the actual relevant context is not in the knowledge graph, right? Which means that the contextual recall and potentially the contextual precision will be low. A fourth problem is when we have knowledge that is irrelevant and redundant, right? So in many cases, a knowledge graph can contain knowledge about multiple domains, about multiple scenarios, about multiple types of questions. When we feed the whole knowledge graph to our application, then we practically stress, let's say we assign high responsibility to the retriever to find the really relevant context, the really relevant knowledge for the question at hand. So in that sense, it might be better if we are able to, if we know that we work on a subdomain of what the knowledge graph contains and only pick that knowledge instead of feeding it to the complete knowledge of the knowledge graph. And the same argument applies for when we have inconcise knowledge. Inconcise knowledge is when the knowledge graph contains duplicate or near duplicate and redundant elements. Especially when it comes to entities, this is a typical problem. Imagine having built a knowledge graph about organizations and about people, and having, for example, 2 different nodes or 3 different nodes representing the same company or the same person, right? This kind of redundancy can pose a problem to our GraphRAG application, because the knowledge about a particular entity will be split around, and can be difficult for the retriever to pick it all up. Finally, a sixth problem is when we have knowledge that I call incomprehensible. Incomprehensible means that the knowledge graph contains elements and assertions whose meaning cannot be easily understood by humans. And by elements, I mean relation names, the way we the names of our labels, the names of the properties, which can be ambiguous, highly vague, highly obscure as to how they mean. And if we think an LLM as being, let's say, I don't like to anthropomorphize things, but the idea is that the LLMs are able to work by natural language. If the descriptions and the names in our knowledge graph of our elements, of our nodes, edges, and attributes cannot be easily understood by humans because they can be too ambiguous or too vague, we cannot expect the LLM to be better than this. So there's a high chance that if that's the case, that the LLM will also fail properly understanding what the knowledge graph is about, and therefore not and bring wrong results. Now, all these issues, all these types of issues in a typical knowledge graph management life cycle, right, need to be tackled, need to be detected as potential problems, quantified in some extent, and then, of course, mitigated and treated. When it comes to knowledge graph detection problems, there are 3, let's say, categories of approaches. One first approach is to try to apply, to define and apply logical constraints and axioms. So, for example, we can, let's say we have a knowledge graph of events, and each event has a start date and end date. We can and we should actually have a rule saying that, or a constraint saying that, you know what, an event's end date cannot precede its start date. Actually, this is something that happened to a real use case that I worked on a couple of months ago, right? Or having another rule like a person cannot also be an organization and things like that. Now, these logical constraints and axioms can really be useful, but usually they are not enough. They're not enough because not all types of issues can be logically expressed and prevented. For that, we need to move to things like heuristics and soft rules. Heuristics and soft rules are rules which are not, which if they, let's say, if they are violated, they don't always mean that there is a problem, but that there is a high chance that there is a problem. For example, let's say that we have 2 nodes, 2 entities in our knowledge graph, whose names have a very high semantic similarity, more than, let's say, 0.9 or 0.95. Then there is a high likelihood that these terms are probably referred to the same entity. Not necessarily, right? Not always, but there is a high chance, which means that we can use this as an alert to for further inspection and checking. Or another example would be to have a movie knowledge graph where each movie has, let's say, less than 3 actors in average. That's probably a problem, because we know, right, it's common knowledge that in the majority of the cases, a movie has more than 3 actors. Of course, there are movies with 1 or 2 actors, but it's not the majority of that, right? So a heuristic like that could indicate completeness problems, for example. And of course, we can be even more sophisticated and try to and go on and build more like machine learning based error detection techniques, including, for example, asking an LLM or building our own error detectors and classifiers, right? Like, for example, we want to tackle ambiguity, we can ask an LLM to flag ambiguous relations. My recommendation there, my experience shows that we can already do a lot of things with the first 2 categories, right? Logical constraints and axioms, and then some basic heuristics and soft rules. And For more advanced cases, we can and we should go for building more sophisticated AI and ML error detection systems. So let's wrap up. I think the takeaways from this, what I would like you to keep from this talk is that GraphRAG is indeed a worthwhile approach to grounding large language models with factual domain knowledge. There's no doubt about that, at least in my experience. But GraphRAG quality can severely be diminished if the quality of the underlying knowledge graph is low. And we saw at least 6 ways that the quality of the underlying knowledge graph can be compromised. Therefore, it's imperative to assess, both when we build the knowledge graph and also as we maintain it, so continuously, to assess and improve the quality of the knowledge graph when using it as a part of a RAG application, right? Especially if we have built the knowledge graph completely automatically, if we have generated from text or other resources. Okay, so that concludes my talk. Before going to questions, I would just like to let you know that if you are further interested in the interplay between knowledge graph and large language models, so more about GraphRAG, but also on how can we use LLMs in order to build knowledge graph, there's a live online course that I will be giving next month at the O'Reilly Learning platform. It's a total 6-hour course where we're going to visit the whole life cycle of knowledge graph development and how can we build, evaluate, and debug GraphRAG applications. So thank you very much for listening to me. If you want to contact me, you can contact me through email, LinkedIn, and also if you're interested, I encourage you to join my Substack newsletter where I give more information and content about these aspects. So thank you very much. Please let me know if you have any questions. Okay, so I see a question. Can you give an example of a knowledge graph for medical reasoning? To detect errors in the relationships, can you use an LLM as a judge? Yeah, so indeed we can have a knowledge graph for medical reasoning that could, for example, relate symptoms with potential diagnosis, with other kinds of patient information, etc. And to detect errors in the knowledge graph, of course, yes, we can use an LLM as a judge, right? But I would say that, as always, when it comes to using LLM as a judge, we need to judge the judge as well, right? So it's not enough to say, to give, for example, let's say that you say to the LLM, okay, can you tell me if this relation is correct? We need to give it proper context also there, right? And additional guidelines on how to properly judge it. Okay, another question. Assuming that the GraphRAG system is able to extract knowledge through ETL processes and distill data to the knowledge graph, does it mean that manually pruning the graph would be a smaller workload for people? And can the results of pruning serve as a mask template condition map for GraphRAG knowledge extraction to increase its focus on most relevant data? Yeah, actually pruning, guided pruning could be really useful, yeah. To see, if you think that if you don't need all the knowledge for that. And actually, let's say as a more advanced GraphRAG pattern could be that this pruning to happen based on the types of questions you expect to receive. Right. Another question. When the domain and therefore schema is not fixed, it is hard to define logical restriction. I guess in these cases we're restricted to heuristics and LLM as a judge. Yes, if you operate in a very open domain, indeed, it can be hard to a priori define these what to call them? Sorry, yeah, these logical restrictions. On the other hand, what I would suggest, it could be that, as you do error detection, error analysis, you might see some basic patterns of errors that could be prevented by enforcing a schema later on, right? Or at least a part of the schema, not necessarily the complete one. Okay, I think we're done. Thank you very much.